Hello, I'm Henry Spoor,
I'm Connor Burns.
and this is our final project for digital electronics. We built a set of circuits, the first of which is a photodiode detector that sweeps a 180 degrees and returns to the point at which it detected the most light. Our second circuit is a four-function calculator. We also had to include a 2 to 4 decoder to reduce the number of I/O pins on our Arduino. Both of these functions, the photodiode detector and the calculator, can have the results displayed to this LCD display. And our final circuit that ties the entire thing together is this switch, which allows us to toggle between which of these gets displayed to the LCD.
So one of the main goals of this project was to demonstrate the versatility of an Arduino. So fundamentally, an Arduino is a microcontroller, which is like a very, very low-powered computer. And part of what makes computers special is how general they are. So our project demonstrated this not only by implementing sort of a calculator, which you can input any two numbers within reason, and it will compute something about them, but we also showed that it can implement arbitrary logic depending on what inputs it's receiving. So we can change this switch, and it will completely change the sort of calculations it's doing. So with the calculator, it's doing multiplication, addition, subtraction, those sorts of operations. And then with the servo, it's doing like duty cycle calculations and minimum maximum calculations and floating average calculations, that sort of thing. Internally, the Arduino Uno is powered by an Atmel Atmega 328P. This is a microcontroller device. It's this large chip here. And this is what actually executes the instructions that are specified in the program. So this microcontroller usually operates anywhere from 1.8 volts to 5.5 volts. In the Arduino Uno's case, it usually operates right around 5, since that's what the internal voltage regulator will regulate it to. And that means that if you're powering this off of a battery or some kind of external power source, the Arduino Uno usually expects anywhere from 7 to 12 volts as an input, and then all of your digital I/O will run at 5 volts, just like the microcontroller. It's also worth noting that each digital output can produce a maximum of 20 milliamps of current at a time. And in total, there are 14 digital input-output pins, 2 of which are hooked up to a hardware serial interface. So this allows you to communicate over a serial port with some other device. So in our case, we usually debugged with a computer, but this could just as easily be another Arduino or a sensor of some kind. We ultimately ended up having to use one of these serial digital input outputs, which meant that we couldn't communicate with the Arduino over serial in our final project. Additionally, there's 6 analog inputs, which you can see each of them here. And these have a 10-bit resolution, which means that there are 1024, or 2 to the 10, different steps, different measurements it can make. So then the microcontroller, the Atmega 328P, internally it has 2 kilobytes of random access memory, as well as a 32 kilobyte EEPROM, which is used to store the program. And that way, the information about the program isn't lost when it loses power. It's able to save it for when it's powered up for a second or third or any number of times later. It also includes an 8 megahertz clock internally, but the Arduino Uno right here has a 16 megahertz external crystal oscillator, which serves as its clock. So the microcontroller will run a little bit faster when it's in an Uno.
So the first circuit of our project is this photodiode detector that sweeps a full 180 degrees and records the highest received light signal using a voltage divider, and then that signal gets displayed to this LCD display.
So you can see it scanning right now, and then it will return to the position of the highest light for about 5 seconds.
And then we'll show with some artificial light that can act as like a sun, for example. Alright, so the way that we implemented this in the code is that we had a function that sweeps our servo motor, and then the entire time it's sweeping, our photodiode detector is outputting a signal. We then capture that highest signal value by calculating the greatest voltage that goes into our analog pin. We then return the servo back to that point with a simple bit of code.
So one of the unintended consequences of how we programmed this calculator is that it actually supports one input being negative. So what I mean by that is there's no way to type in a negative number on the numpad, but if you type in an expression like this, 32 minus 56, the answer is going to be less than 0. And so if we perform this operation, you can see we get a negative number in the first number slot. And so these negative numbers behave exactly how you would expect them to. It's just that since you can't input them by hand, you could never say add or multiply two negative numbers together. And this just is because we implemented each of the numbers in the code using integers of length 32 bits. So you can see operations work just normally. Another thing we didn't mention earlier was that we implemented a delete function, so inevitably the user will make a mistake, and we can undo that using the star symbol. So you can see here, if we start with a number, you can get rid of its contents using the delete button.
So for our LCD display, we have this potentiometer, which can change the contrast of the display. So if we change this a little bit, you can see that the numbers become more or less visible. So we found that this was a good setting to easily see what is being displayed to the LCD. And then the last component of our project is our switch, which determines which of the two circuits is displayed to the LCD. So we'll demonstrate this functionality for a little bit. Currently it is in calculator mode, and we're going to switch it to the photodiode detector. And then we'll let this run one more time, then switch back to the calculator.
Now we're back in calculator mode.
And we can perform all of our calculator functions as we showed before, and then we can switch back using the switch, and we can record new values for our photodiode detector. We'll demonstrate it having an artificial light source again. And that is our project. So some of the limitations of the project, obviously the Arduino has a limited number of I/O pins, and we exceeded that amount just with the calculator and the LCD display. Therefore we had to include our decoder.
And even with that improvement, we still had to overflow and use our 1 pin, which is actually built into the Arduino to be TX. So at the end, when we were putting everything together, we couldn't use the serial monitor anymore. And then the second limitation we encountered quite a bit when building the 4-function calculator was with the numpad. So like I mentioned earlier, not only, well, you can't press more than one button at a time, which wasn't a huge problem for our application. But another error or issue we encountered was that the multiplexer we used would actually output one low and then the rest high, depending on what our input binary number was, which meant that our algorithm for determining which pin was pressed was very strange and a little bit unstable at times, because when you bend this thing or really apply any sort of force anywhere, the contacts change a little bit and it'll give you a different value than what you might expect. So our algorithm had to be quite versatile to this consequence of the multiplexer being inverted. So we had to take an average over time to address that.
And then a final limitation that we had was that our servo would draw lots of current to perform its rotating function, and this would cause our Arduino to have unexpected behavior from the voltage signal being so, it was sporadic, that's a good way to put it. So we included an external power supply to take care of this problem, and we just connected the power of our servo to the external power supply, and we saw a reduction in the noise in our Arduino.
Perfect.
So our conclusions for this project are that we were successfully able to debug any problems that we encountered while designing the project, such as having to reduce the number of I/O pins that we used by using a decoder chip. We also found that the versatility of the Arduino board is exceptional, and we demonstrated this by taking 2 completely different functionalities, and we're able to combine them into a single project where we can toggle between the functionalities and have a successful circuit.